Hey everybody, and welcome back to Algebra 2 online. I wanted to just start and do another absolute value inequality today. So anytime I do one of these again, I would recommend you pause and ponder, try and work them out on your own. And I'm just going to jump into it. Hopefully you have time to pause. So the problem here, you could simplify it a little bit right off the bat. You could add... Oh, that's not a good color. Let's do that again. You could add that 1 or negative 1 over, right? We get negative 3. And hopefully you see right away that this thing is going to have no solution. The idea is like this part over here, definitely a positive number, right? And you've got a less than a negative number, right? And that's impossible. You can't have any positive number be less than a negative. The reason this part over here is positive again is just that absolute value measures distances, so it has to be positive. So today, the main goal that I want to talk about is the idea of functions, and specifically input, output, domain, range, these kind of things. Hopefully you've heard these words, but you maybe haven't heard them in a few years, like depending on if your geometry teacher talked about them or not. But we will definitely talk about it a lot this year, so I want to make sure you're familiar with all these. So the words input and output are fine. I will talk a little bit that there's kind of a more mathy word for these things, but I want to start and just take these two kind of pictures here. So on the one on the left, think of these as your inputs, and think of these as your outputs, and these as your inputs, and these as your outputs. And a function that is one-to-one, like this picture, is a very nice function. And we'll talk a lot more about why that's so nice. But something that's not one-to-one could be like this example. So here, we would actually call this thing 2-to-1 because there are 2 inputs that go to 1 output. This part being one number to one number doesn't make the whole thing 1-to-1. You have to look at kind of what the biggest relationship is. And here, the biggest relationship are these 2 things going to this one thing. But here, every single thing just goes 1-to-1, 1-to-1. These are really, really, really nice. And over here, I'll kind of draw an example, or 2 examples, I guess. So something that is 1-to-1, like, is something you study a lot in Algebra 1, and it's like line. Specifically, actually, diagonal lines. So we'll talk in a second, actually. If you do a horizontal or a vertical line, it's not going to be 1-to-1, actually. So any diagonal line would be 1-to-1. And the idea is just you could take, this point here, and there is only one input that goes to this one output. You could do that anywhere you want on this line. Down here, this one input goes to this one output. There is nowhere that you're going to double up. Something that is, so this one, again, I should probably be right on this one is 1-to-1. Something that's not 1-to-1, let's take a quadratic. So if I take x squared is actually what we would call, this one down here would be 2-to-1. And it's 2-to-1 because I could take something like, negative 2, and I could take 2. And if I square negative 2, I get 4, right? And if I square 2, this is a bad picture, but I also get 4, right? So 2 different inputs there are going to the exact same output. So we would call this thing 2-to-1. And maybe I'll also add, there are things out there that are like 3-to-1, 4-to-1. There's things that are like 1-to-3 and stuff. So maybe just to draw one more example, like if you do, I don't know, how about something like that. We actually will graph some things like this later on. And this right here there's 1, 2, 3, 4, 5 spots where you have different x values, but you have the exact same output. And so we would call this 5 to 1. That would kind of be the biggest relationship you see. There are parts like over here and over here where it would be 1 to 1, but since there's a spot that is 5 to 1, we call this thing 5 to 1. So these two questions are just kind of good ones to think about. And again, I recommend you stop and try to come up with answers before I just jump into it right now. So kind of weird examples, but there are things that are infinite to 1, and there are things that are 1 to infinite. And the simplest thing to do here is just to take a horizontal line for infinite to 1 and take a vertical line for 1 to infinite. There are, in this first example, a whole bunch of points here, infinite amount, and all those points just go to this one output right there, right? So that would be something that is infinite to 1. And the other, the reverse direction is kind of happening down here. So if you do, if you take this one input goes to that output, it goes to that output, it goes to that output, and that output, and that output, right? So you get all these different outputs that just go to this one input. So this is something that's 1 to infinite. And in math, we don't mind things that are infinite to 1. You maybe think that's a bad function or something, but this is actually a perfectly well-defined function. This thing down here, this is not well-defined. And the way I always think about it is you wouldn't want some function in the world that, you plug in one thing and you get out a bunch of different things. Take like temperature. If we were converting Fahrenheit and Celsius, if we plugged in 20 degrees Celsius, we don't want 20 degrees Celsius converting to infinitely many different Fahrenheit temperatures. That would be really confusing, right? So this is something that we will talk about more, but this is actually not good in math. This one's fine. This thing's going to be totally fine. And so I've kind of tiptoed around these words, but now I want to just put them out there. So when we have functions, the input world, really the fancy word that I'm going to say all the time is domain. So domain is really what you'll hear me use for all those x values, all those input values. And when I talk about the outputs, I really will say the range. That's your y values typically, right? So if we think of like function notation, f here operates on x's, your inputs, and gives you out this y output, okay? But these terms, domain and range, really just fancy words for input-output. So the domain is all the input values you see in the function, and the range is all the output values. So just to kind of show how I could ask you a question like this. This is actually a graph of a sine wave, and we will graph these way at the end of the year, not for a while, but they are an infinite wave that just goes on and on and on like this forever. Its max height is 1, its lowest height is -1. And if we were asked to find the domain and range from a picture, basically for domain, my brain just goes and looks on this axis, right, your x-axis, and I can see that it just kind of keeps going and going and going and going like on a wave like that forever. And so the best way to answer this one would just to use that weird R. So all real numbers would work for that, the domain there. There's no number you can't plug in, basically. The range is not like that, though. So for the range, my brain just kind of looks up and down now. and I'm just kind of looking to see what type of y values do I see in the picture, right? And there aren't infinite, right? Like I never get to 2, I never get to 3, I never get to 4. So here, the best way to do it, there's 2 ways that I guess are both good. So one way, you can just use inequalities. You could say -1 is less than or equal to y, which is less than or equal to 1. You definitely need the y there because we're talking about y values. The other way that's perfectly okay to do this is to just use interval notation. So hopefully you saw some of this back in Algebra 1 also, but I might do something like that. And that's just saying really the same kind of thing. It's just saying everything from -1 to 1. That's what the square brackets mean. That includes the -1 and 1. So I talked about this kind of 2 slides ago, and I wanted to just kind of formalize what I was saying. So in these 4 pictures, one of these is not a function, but the other 3 are. And I would definitely encourage you to stop and think about which ones you think is not a function. A lot of times, students don't like this one down here. This point is actually perfectly, I flipped slides there, sorry. But it's perfectly okay. There is no issues with that point, actually. The one that's actually bad is down here. It's this smiley face. And this is something you learn about in Algebra 1, but it's been a while, and I realize you might forget some of this stuff. This guy down here fails something called the vertical line test. A lot of times they just call it the VLT, okay? And it's basically just a test to see if a relation is a function. And it fails because you hit, I guess I'll do some red, you can hit 1, 2, really even 3, 4, 5 different points there with a vertical line. But in all the other ones, if I draw a vertical line anywhere, right, here, that spot, this spot, right, I'm only ever going to hit 1 point. And so basically the way I tell students to do this is like take their like pen or pencil and you kind of like sweep it across the graph or the picture. And if you can find anywhere where the vertical pen hits more than 1 spot, it's not gonna be a function, okay? And I always just, again, think of it kind of back where I was talking about this vertical line here. This doesn't make sense in the world, right? We don't want things where like 1 Celsius degree could convert to infinitely many different Fahrenheit degrees. That would be very weird. It's just realistically, it's not a good, useful thing for us. They do show up. I mean, we can graph a circle. I did this on a computer to make this picture, but it's just not a function. We call those things relations, not functions, basically. So points are fine. A lot of times students don't like this point, but you can have a really simple function that just maps 4 to 2, and that's it. That's perfectly fine. The sine wave is a function. This is the line y equals x. Perfectly good function, no issues there. But this one down here, this is the bad one. And it's just bad because it hits more than 1 spot with a vertical line. So this is the last thing I just want to do, kind of combining everything we just talked about. So I have a weird graph here where I have a vertical line segment from -1 to 1 and a point at 2, 1, and then a point at 2, -1. And maybe just to make this a little more clear, let's make all these blue, just not confused. So the domain, right, again, I would just look left and right. And I can see that I go from -1 to 1 on the line segment. So you can do that. -1 is less than or equal to x, which is less than or equal to 1. And then I also have x values at 2. So I'm going to just write literally in words, and x can be 2. Right? That sums up all the x's I see. These spots show up on this line, and 2 give me these 2 points, right? But there's no 1.5, there's no -1.5, nothing else there. For the range, I would just look, now on the y-axis, and I can see I get a -1 and a 1, so y can equal -1 and 1. And I also get 2, but that's it, right? So if you just have a few y values that you see in the picture, just literally list them like the way I did here. You don't want inequalities because you don't want to say all this stuff between them also, just these 3 points. And the last question down here, is this thing a function? So over here, okay, this passes the vertical line test. That passes the vertical line test, but over here, right, I have these 2 points stacked on top, and this is sort of like the minimum issue needed to fail the vertical line test, but back before when I drew a vertical line, that's like your worst case. Like this thing fails it horribly because there are infinite amount of points stacked. But here, still fails because there's, this spot shares the same exact x value as this one, but they have 2 different y values. So the answer to that last question is no, and it's really because of that vertical line right there. And that is about it for today.